So chapter 5 is about something that's not completely new, but it is a definite, let's call it a 180-degree turn from what we've been doing up until this point. So chapter 5 starts with 5.1, which is where we will introduce the idea of antiderivatives. And they are exactly what they sound like. They're the exact opposite of a derivative. I haven't, this is the first time I fired this on today. Let me just adjust the focus and make sure that we're focused properly. I think that looks about good. So it's the exact opposite of a derivative, and that's going to come right out of this definition. So the way we'll say it is a function f, and I'll specifically say a function capital F is an antiderivative of a function which we'll call little f. So this is typically the function you would look at originally, and then you would say what it means for a function capital F to be an antiderivative of it. And the definition is capital F is an antiderivative of little f if when you take its derivative you get little f. Right? That's what the definition is. So it's just if this happens to be the derivative of little f, then it's called an antiderivative of little f. So let's just look at a couple of examples. And I'll write expressions involving a variable x, and we'll interpret them as functions of x. Because this is a definition that applies to functions. So for example, x squared is an antiderivative of 2x. Well, how do you verify that? Just because I say it doesn't mean it's true. Well, you would use this definition. I'm claiming that x squared is an antiderivative of 2x, so the way you would check that statement is you just differentiate x squared and see if 2x is in fact what you get. And of course the answer is yes in this case. So that's why we can see that x squared is an antiderivative of 2x. Another example, sine of x is an antiderivative of what? Remember, whatever function I put here, when I take the derivative of sine, I had better get this. So you can conclude that the right function to put here is cosine of x. So, and indeed, sine of x is an antiderivative of cosine of x, because when you take the derivative of sine of x, you get cosine of x. I'll just do one more example, and we'll make another comment. Negative cosine of x is an antiderivative of sine of x. And just stop and make sure you agree with me. How do you know that negative cosine of x is an antiderivative of sine of x? Well, if you take the derivative of negative cosine of x, you'd better get sine of x. And if you get anything else, then this statement is false. But of course, if you do take the derivative of negative cosine of x, you can check that you do get sine of x. Okay, so a remark about this last one in particular, there are actually many other antiderivatives of sine of x. And in fact, there are many other derivatives of cosine of x or 2x, and any function at all actually has infinitely many antiderivatives. Let's look a little bit more closely at that. Let's focus on the last one, though. There are many more antiderivatives of sine of x. Let's look at a few examples. So how about negative cosine of x? That's the one I just said. But how about negative cosine of x plus 1? Is that an antiderivative of sine of x? Well, how would you test it? Well, if you take the derivative of this function, do you get sine of x? And the answer is yes, because if you differentiate cosine of x, you'll get negative sine. So that extra negative sign turns it actually into positive sine. And this extra plus 1 doesn't really change anything, because if I take the derivative of positive 1, or plus the plus 1 term, if you differentiate it, just disappears and becomes 0. So the derivative of this function is still sine of x. And there's nothing special about 1 that makes this work. For example, if I went negative cosine of x plus 10, that would also work. And it really just comes down to the fact that if you differentiate the constant, it disappears. if you differentiate negative cosine of x minus 100. It doesn't have to even be a positive constant. It could be any constant at all. Differentiate this function. You're still going to get sine of x. It doesn't even have to be a nice whole number. If I had negative cosine of x, how about plus pi times e squared divided by the square root of 2, just to be particularly obnoxious. That would also be an antiderivative of sine of x, because if you differentiate this term, it becomes 0 because it's constant. It doesn't matter that it's ugly. It's just a constant. And in fact, the list goes on forever. In fact, you can't even get them all in a list. There's just infinitely many. So the list goes on. I messed this one up. The list goes on. Okay, so let's introduce a little bit more terminology. I'll squeeze it in up here. So if f is any antiderivative of little f, then we can talk about something called the general antiderivative, which really just takes all of these examples, plus all the ones I would get if I kept on trying to list them all, and it groups them all together into one concept. And it's called the general antiderivative. So we're starting with the assumption that capital F is just one particular antiderivative of little f. And then we're giving meaning to the general antiderivative, or also, this is sometimes referred to as the indefinite integral. That's another term. Of the function little f is given by capital F plus just this c here, where we use c really just to represent some arbitrary constant. So let me put that in. I'll say where c in the reals is an arbitrary constant. So it could be anything at all as long as it's constant. And the notation that we'll use the notation for this as follows. We'll actually write our function little f. This is the function that we're trying to describe the general antiderivative to. And there's two pieces of notation. You'll first write this symbol here, which almost looks like a really tall, skinny S that's been stretched out. That's called the integral sign. And then then you'll also write a dx at the end, just to indicate that you're talking about the general antiderivative of f of x with respect to the variable x. Just like when you take the derivative of a function, you specify which variable you're taking the derivative with respect to. You do the same thing when you're talking about the general antiderivative. And this is defined to be capital F of x plus c, where capital F is the function up here, which was a particular antiderivative of the function little f. So if you take a particular antiderivative of a function and you add this general constant, you get the general antiderivative. One last thing before I will end this particular clip. In this case, we have a name for c. It's called the constant of integration. So that's the definition of a general antiderivative, and we'll do some more examples in the next clip.